Okay, so now we're going to discuss chapter 5, which is called Managing Vector Data. So in the newest version of the book, she's kind of separated this with the vector data and then chapter 6, which is the raster data. And what this is sort of the do's and don'ts for handling vector data, that is points, lines, and polygons. So throughout this chapter, we're going to look at what is vector data, how to save it, where to save it, what file types to look for, what is everything called. So there's some definitions in here, there's some jargon. Make sure you start to understand what these things are because it'll make going forward much, much easier. All right, so I mentioned this back in I think chapter 1. So vector data are stored as XY pairs, kind of like a Latin line sort of thing, but not necessarily in latitude and longitude. And each XY pair is a vertex, or for vertices if you have more than one. So you have points, lines, and polygons that make up these vertices or end nodes. And the program understands where to place them both in space and on screen, so to speak. Now, you can have multi-part features. And what that means is it's the same thing but in separate polygons. For example, Hawaii, right, is made up of multiple islands. All right, so you wouldn't want that way you could sort of differentiate between the islands, but they're still all called Hawaii and they only take up one row in an attribute table. So attribute tables are where the data is stored. It links the tables to the data, and the attributes are the columns, so they describe each one of the pieces of data, and the data are the rows, the records. So you'll notice that each table has either a feature ID or an object ID, depending on whether it's a feature class or a standalone table. And those are sort of unique identifiers, typically just ascending integers, 1, 2, 3, 4, 5, 6, 7, 8, 9. You get the idea? That allow you, it's a numbering system for the database portion of GIS. So the rows are each piece of data that's sitting on your map, every record, and the columns are the attributes, which are the descriptors that tell you what's going on for each row. So for example, if you take this first line in the attribute table, we have the state of Washington here. All right, it's a polygon. The shape field, the second column in the shape field, is automatically generated. It can't be changed, it can't be modified. That's the program's way of telling you what the geometry is in that attribute table. You cannot mix and match geometries. So if you have polygons, everything in there will be polygons. If you have lines, everything will be lines, and if points, you'll have all points. So that's the shape field. It tells you the geometry. And then from there, you have all kinds of columns of varying types depending on what your data type is. So for this one, we have the state underscore name, and we'll get into naming systems in a bit. You have state FIPS. FIPS is the federal identification protocol thing. I forgot what it stands for. I think there's a slide later on. It's basically a unique identifier for each state, and also each county has one as well. You have the subregion, and then you can go on from there. Now, attribute tables can get quite big, both in terms of the number of rows. You can have millions of rows, or the number of columns. You can have thousands of columns if you have that much data to describe each row. So a lot of the data that we use in this course is census data that's been taken probably from the previous census, the 2010 or maybe a slightly updated one. And so it has all kinds of demographic data in there for each state and each county for the county's attribute table. So a feature class is a collection of similar features stored together as a data set, like the states. So when you open the attribute table, you're opening a feature class, and therefore the feature class is the same thing of that particular set of data. So all the states or all of the counties or all of the cities, all of the roads, they're clumped together into a common feature class with one big attribute table with all of the various columns describing the data. Now, like I just mentioned, feature classes can only contain one type of geometry, which makes life very much easier. You wouldn't want to mix and match these things. Now, there are different types of formats. Some are older and some are newer. So things like shapefiles and geodatabases. We have a tendency to use geodatabases almost exclusively now, although there are still shapefiles out there, and even once in a blue moon, some older formats, which we'll go through very quickly later. So a simple vector data format is called a spaghetti model. Each state is stored as a separate object unrelated to the others. So the adjacent boundaries are stored twice. So in the background, you don't necessarily see this in the attribute table. It has the boundaries for both the state and the state next to it, so to speak. It's a robust model because of its simplicity, and it's the most common used model. It's pretty much the only model we're going to use in this course. So when you're moving data around and you're manipulating it, just know that you're actually utilizing this what's called spaghetti model. It's the simplest one, and it doesn't require much maintenance. It doesn't require any maintenance actually. The other type of model is what's called the topological model, where you have to maintain data integrity utilizing the tools found in a geodatabase. So things like testing for adjacency, connectivity, do roads connect correctly? Do rivers connect? Overlap, you don't want any overlap with your states, intersecting roads, things like that. And the idea is that by setting up topological models, you adhere to these rules. You can't even mess with it. It won't even let you if you set it up correctly. Therefore, you always know that your states are adjacent, your roads are connected correctly, or your network, whatever you're trying to get at. So that this is a bit more um, of a hands-on type of model. You have to set this type of stuff up. But in places like city government and county government, this is what they use to ensure data integrity. So somebody can't just go in there and create some overlap or a gap between state boundaries or things like that. Okay, so GIS data in general are different than, let's say, other types of data. So, for example, the files can be very large, especially with rasters. They could be gigs. They're often shared by multiple users. If you're in an environment where you have an enterprise system, you have to sometimes check in and check out data where you have multiple people using it. For our purposes, you're going to be working isolated on your own desktop or laptop, so that's not a problem. They come from many different sources. I've already mentioned some throughout the slides, like the USGS, the soil survey, NOAA for precipitation data, NEIC for earthquake, or IRIS for earthquake data. It goes on and on. All the state agencies, the federal agencies, the city agencies. There's just so many different sources that you can get data from. Sometimes they're on a local computer and sometimes they're on a file server or online source. The easiest way to learn GIS is for sure kind of keeping it local on your computer so you can tinker with it. A lot of the data that's found online is strictly for viewing. It's not necessarily for being able to download or just do anything with. It's strictly just sort of a pretty background. Um, some of the data you're going to find, not too much anymore. I haven't come across too many, but they don't always follow the latest and greatest file conventions. One of the things about GIS over the years that I've been doing it is they've been steadily upgrading their sort of standards or minimum standards, if you will, for the data types that they prefer you to use. So when I started, we were just using what are called shapefiles, and I'll get into this in a second. And they've since moved on to geodatabases. And some of these formats can be complicated, like geodatabases can be, and I'll explain that in a moment. So here's some tips for managing your data. Be organized. I have data on network drives, my internal C drive, external hard drives that are a terabyte, or like actually they're 3 terabytes. I have data all over the place. The reason I can find things is I have things well labeled. It's huge. You have to stay organized. Okay, making a folder takes 2 seconds, but it can save you a lot of headaches if you can't figure out where you put stuff later on. I work on a lot of projects where I may work on it and then put it aside for a couple months at a time because I got to do things for teaching, or I have other projects that pop up that take priority. So I have to go back and be able to remember A, where it is, and B, what I did. And keeping things organized is a great way to be able to pick up where you left off, so to speak. Do not use the desktop or the document folders. I strongly suggest if you're using your own laptop, put it directly on the C drive. If you're on a departmental computer, there's a place on there that you can add folders in the lab, or if it's in your office, just use the C drive like I just mentioned. Just always try to keep it at the root. It keeps the path names short, which we'll talk about in a second. Just keep it, don't put it on the desktop, don't put it in documents, because those things get garbaged up very quickly. You also want to use descriptive names with your file types. Now, the example she gives here is the snail habitat, okay? So this is an output for what's called the raster calculator. All right, so by default, the first time you run the tool, if you just left the default name, it's going to be raster calc 1. Well, if you run it again, guess what? Yep, the file name will be rastercalc2. So if you don't give your files descriptive names, excuse me, then it can really be hard to go back and figure out which one you actually needed. This is also another reason why it's sometimes very handy to allow you to just overwrite your file. Just if you screw it up, which you probably will at some point, you got to get the outright output at some point. Maybe you just missed a setting or something. Just overwrite the previous file rather than create 15, raster calc 1, 2, 3, 4, 5, and trying to remember. I did that years and years ago, and it's frustrating. I stopped doing it. So now I name them right away, and if I screw something up, I just overwrite the one I screwed up. Another thing I do typically is I try to keep things separate. So when I'm working on, for example, the class, I have a geodatabase with sort of the blank slate stuff, the stuff I would hand to you, and then I have another version for myself that if I need to test things or whatever, I can do that. So it's nice to have sort of an original copy, either zipped up or laying around. Same thing with anything that you download. So put downloads in a separate folder. Keep the zip file. I can't stress that enough. Nothing's worse than saying, "Oh, I don't need the zip file." You delete it, you empty your trash, and then you realize you screwed up your data. Now you got to go back out to the website if you can remember where you got it. Go re-download it, re-unzip it, and all that stuff. There should be plenty of space on all your hard drives for most of this stuff. Just keep the zip file, so if something goes wrong, you can unzip it and voila, you have a fresh new copy of the data. And I strongly suggest that for the course data as well. So there are some pretty strict naming conventions. Never, ever, 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 ever use spaces in folder names. All right, just get out of that habit now. Not ever, anywhere, nix, no, nine, yet, none. Okay, so use the underscore. If you're doing a project called snail habitat, put snail underscore habitat. That is perfectly cool. Use the underscore. Try to keep the folder name short but descriptive. You know, because what happens is, especially for rasters, not so much for vector uh, operations, but a lot of the raster stuff was developed way back in Unix days. And if you've ever used Unix or Linux, you know right away that it does not like spaces and path names. Weird things can happen. So it's just a habit. I use it for pretty much everything now. I've been doing this so long. I just automatically add underscores in between everything. That way I just always remember to do it. Um, if you don't do it, sometimes what happens is the computer doesn't recognize where you put it, and you can sometimes really screw things up. The other thing is like I said, when you're doing raster work, if you have spaces in your path name, a lot of the tools will strictly just, they'll throw you an error and it'll drive you nuts until you figure out, hey, I have a space in my path, and that will do it. That's enough to cause the error that will not allow that tool to run. Never, ever, ever, ever use spaces in folder names or file names. Just get in the habit of using the underscore. So one of the things with ArcGIS that can confuse people is most of you have seen some of the more common file extensions like a .doc or .docx. You know, that's Word. You got the XLS and XLSX, which is Excel. Okay, but you know, there's some that you're going to see that you've never seen before. Maybe you've never done a zip file. Who knows? So what you have are things like the .mxd. That's a map file. Okay, although it's changed now a little bit in ArcGIS Pro, but a .mxd file is a map file created by ArcMap. A TIFF file, maybe you've never heard of that. It's an image format that's lossless. What that means is you know, when you take a picture with your phone, the it comes out as a JPEG, and a JPEG is a compressed version of real life, so to speak. Even though you might have millions of megapixels, you're still losing some granularity because of the algorithm that compresses the file to keep the file sizes in line. A TIFF does not do that. You get back the all of the information, and therefore those file sizes can be kind of big. And a PNG file, if you don't know, stands for Portable Network Graphics. It's similar to a JPEG. However, it does allow for transparency. So those are used quite a bit on the web. They're really nice. I use them all the time. Um, if you don't see the extensions, you can go into your folder options in Word and Windows and check to make sure that they're on. It does really help to see the file extensions so you know what you're looking at, especially when you're first learning. So another thing that comes into play is when you have data being accessed by multiple users or multiple um, programs. So you can get what's called a file lock if you're in a sharing environment where you have two people that want to use the same file. Again, we're not going to deal with that. I'm just bringing it up for sort of completeness sake. But what you will do is you'll probably run into some point if we're, you know, down the road when we do the subwatershed recharge rate exercise, you cannot have Excel open with the file you're using along with that same file in ArcGIS. You have to close one or the other. So if you're going to edit your file in Excel, that's great. You can have that open. You can do that with ArcGIS open. But once you bring that Excel file into ArcGIS, you have to close Excel. They cannot be opened at the same time. You will get a file lock issue. Okay. So that's just something that you got to kind of keep in mind when you're dealing with Excel spreadsheets. You can have it open to edit it while working on ArcMap as long as the Excel spreadsheet is not in ArcMap while the Excel spreadsheet is open. Another hugely helpful tool is zip files, right? So they're compressed directory structures or even compressed files that allow you to easily move entire directory structures seamlessly and painlessly. On most computers for UWM, you have what's called 7-zip. If you don't have that on your personal computer, go get it. It's awesome, it's free, and it unzips darn near everything. It's a great program. As a side note, I've been doing GIS a long time. Another great program to have is Notepad++. It's free and it will open almost anything. If you get a file and you have no idea what it is, you can pretty much open anything, even binary, although you won't be able to read it, but you can open it in Notepad++. So Notepad++ is a must-have for me all the time. It's just because there are going to be times, especially in raster world, where you have to open up these weird files to look at header information and things like that. And Notepad++ will open anything. It's a great, great free program along with 7-zip. So go get it. All right. So another thing that you're going to do quite a bit that in GIS is you're going to import and export data for various reasons. Okay. Um, Sometimes you want to just convert a file type. Sometimes you want to update things. Sometimes you're bringing in data from, let's say, a comma separated file or an Excel spreadsheet, which we'll talk about later in this chapter, and you got to bring it in. So by the way to do that now, they've changed it in Arc Pro. There used to be well, they haven't changed it totally, but there's a tool called feature class to feature class. And basically what that is you're moving the file from one space to another. Now, let's say you have some older shape files and you want to bring those into your GIS, into your geodatabase. So this is an easy way to do that. Um, you just have to, because it's sitting outside of a geodatabase. You can give it the same name, it just won't have the extension .shp. You tell it what's the input, in this case states. Okay, where's it going? Which, sorry, which is the New Jersey geodatabase, and here's what you're going to call it. Okay, and then there's some other options here, but for the most part, you won't need those unless if you're doing selection methods, which we won't get to for a while yet. Okay, there's multiple reasons for doing this, and this is one of them. Another thing you have to keep in mind, and I've already brought this up back in I think chapter 1 or 2, is the source scale. So if you're doing data collection, you're out on the web and you're trying to find data for your project, you have to keep in mind the scale at which you're working at. If you're working at, having the map way out and showing the United States, then having a very generalized outline of the United States is perfectly fine. If you're doing a detailed coastal study, you definitely want these black lines like this, where it shows all of the detail, and not this purple line, which is completely generalized and doesn't show you anything. So you have to be aware of what scale the data was intended for. Typically, you can find that in the metadata. Now, we haven't talked too much about metadata, but it's data about the data. It comes with your data, and it's a great place to find out everything you need to know about what you're getting yourself into with that data. And I'll talk about a bit more about that in a few slides. Okay, so I mentioned this before. So someone like me who uses earthquake data, I sometimes, when you download earthquake data, it's usually in a CSV format or you got to import it into an Excel spreadsheet. And the columns include the latitude and longitude. And this is very important, the latitude and longitude in decimal degrees. You can't use minutes, degrees, seconds in this. It has to be decimal degrees. And you can see that a little bit here. Those are decimal degrees. So there's a three-step process, and I mentioned this in chapter 4 with the coordinate systems. There's a three-step process. So first I bring in, let's say, the Excel spreadsheet. The program has no idea what to do with it, so I have to tell it, hey, give me use this you want to display it. It says, okay, use this particular tool, the XY table to point. You have to give it the longitude field, the latitude field, and then I typically do not fill this in. This is personal preference, or if you're going to fill it in, you only fill in the GCS, one of three, just like the define projection tool, NAD 83, NAD 27, or WGS 84. That's all that should be in here because the data is in Latin Lon. Therefore, it should not have planar coordinate system attached to it at all yet. Okay, so these are climate stations. They came in as Latin Lon. You have to use the XY table to point, tell it what the longitude is, what the latitude is, and then give it a GCS. I typically don't do this. I add the step in and use the define projection tool after I bring it in, but it's a horse apiece. You can do it either way. You can cut off a step by putting the GCS right in here. Once you have this done and you fill this out, you will then get a permanent uh, sort of record, or excuse me, a permanent feature class with your climate stations. When you first do this, when you first bring them in, they're displayed as what's called an event layer. Okay. So what that is sort of a temporary file. If you go to look at where that particular file is stored, it's stored in a temporary folder. Okay. We want to make it permanent. So we go through the process of running this tool, giving it the Latin LON and the GCS to make it permanent. So when you first bring it in, the program doesn't know what to do with it. You tell it what to do with it and tell it where to save it. Then you will have a permanent feature class of, in this case, climate stations. So it's a little bit of a process, but once you've done it once or twice, it's not a big deal at all. So don't be afraid to use this type of data. I use it all the time for either climate stations, because I've done a lot with that with terroir, or earthquakes. Obviously, I've done a lot with that as well. So there are some data sets out there that have to be brought in this way. It's not hard. It's just a couple added steps. No big deal. Another thing you could do with vector data is what's called geocoding. Now, we're not going to get into that too much in this course. They changed it quite a bit over the last 5, 6 years. Geocoding is taking an address and being able to display it on a map. So if I have all the points of all the houses in Milwaukee, city of Milwaukee, with their addresses, there's a what's called a locator. You need, well, it requires a locator to help you take them from real world into GIS and give them the correct address on your map. However, they've made this a service. Okay. So you can go into ArcGIS Online and do a single address. Let's say you want to find your house, right? It'll allow you to do that. However, if you're going to do multiple, that costs what they call service credits. Now, you can build your own locator. In fact, the people at the UWM library have built a locator for ArcMap. I don't know if they've updated it for ArcGIS Pro, but they built a locator for the city of Milwaukee or the county. I can't remember off the top of my head. So I was able to snag a copy of that so I could use it. I don't use it very often. As geologists or geoscientists, we don't use addressing quite that much because we have a tendency to analyze natural phenomenon. We don't care what the address of a volcano is, right? So this isn't something you're going to do a ton unless if you go into city or county government. There, it's a much bigger deal where you're dealing with parcel data. Now, over in urban planning and the geography department, they probably spend a bit more time on this because they're dealing with what's called parcel data, which is the footprint of each building. So they do a bit more of that than we will. But just know that it can be done. I have not done this yet in ArcGIS Pro. This is something I have not done at all. In fact, I've only done it a handful of times in ArcMap. But it is definitely handy if you can get a hold of or design a locator, which from what I've heard is quite intensive. All right, another huge tool set that you're going to use in GIS from day one is what's called extracting data. So very rarely do you ever download data that fits exactly the area that you need it for. One of the few exceptions of that is, let's say if you're doing all of Dane County, I can download soil data by the county. Okay, so that is designed per county. But very rarely is that the case. You end up having data that sits outside of political boundaries. And what happens is, or if you're working within even a smaller area within a political boundary, at some point in time, you're going to have to whittle down the data you have. That is a huge part of what I call pre-processing in GIS. Before you're going to do analysis, you want to whittle down that data to the exact data you need so you can get rid of all of the overburden, so to speak, all of that other cumbersome data that you just don't need to carry around with you. The way you do this is mainly with queries, which is asking the data a question and getting back an answer. So give me all of the states that start with the letter M. So Montana, Mississippi, you get Maine, you get the idea. So it'll highlight those, and then I can separate those out via, exporting if I want. Another huge tool that you're going to use is called the clip tool. The clip tool is like a cookie cutter. So here's my data. Here's my cookie cutter. So what I get back is just my data underneath the cookie cutter. Hopefully this makes sense right away. If you've ever made Christmas cookies in the shape of Santa, you press down the dough in the shape of Santa and you get back a Santa shaped cookie, right? Makes sense? Now, the thing with this, especially let's say in your final project, is what you want to use for your cookie cutter is where you start. So if you're using Milwaukee County and you're doing all of Milwaukee County for some type of analysis, Milwaukee County is your cookie cutter, and then you will extract or clip, in this case, sorry, clip everything down. You smush down everything to this county of Milwaukee. So we already know that roads and rivers, for example, they don't stop at political boundaries. But with the clip tool, you can chop them off at the political boundary because you don't care what happens to it outside of that political boundary. So that's huge in all GIS analysis. The other thing that does is that by limiting where, let's say, rivers and roads, for example, are cut off like that, it gives us a more accurate measure of, let's say, the length of roads that we have to deal with within the county of Milwaukee, or the length of rivers. So you start to get at things like areas and rivers, areas with polygons, areas and lengths in just the area of interest that we care about. Okay. And so the clip tool is used over and over and over again. It's one of the things when you're first gathering up data for your project, you're going to clip everything down to your area of interest, whatever shape that is. And it doesn't have to be a county. So to use an example, I think it's Mount Rainier or Mount St. Helens. I forget which one. It might be both. It straddles two counties. So rather than download everything for two counties, which you kind of have to do anyway, you can create your own box, a feature class that's just in the shape of a square, and that's your area of interest, and you just chop everything down to that. And that's the way it works with a lot of things. If you're doing vineyard site suitability, I don't care about anything that doesn't include vineyards. I just want where the vineyards are. So I create polygons and I clip and extract everything out from there. Now, the opposite or the inverse of the clip tool is the erase tool. So you going back to the cookie cutter example, if I take my Santa cookie cutter and I push it down, I get rid of what's under the cutter and keep everything around it. So what this does is it kind of creates, let's say, an exclusion zone or something like that. It's not used very often, in all honesty. I only use it in rare occasion. It's not something you're just going to do very often. And at least in the past, with the older versions, this required a higher license level. So it wasn't even available at the basic license level. Maybe it is now. I'm actually not sure. Another thing you can do with vector data is merging data sets. This is not something I recommend doing very often unless if you absolutely know what you're doing. But there are some instances where it's both required and it's not too bad if you know what you're doing. For example, soil data. Let's say I'm doing a project and the unfortunate reality is I need two counties of soil data. Let's say I need Milwaukee and Waukesha. My area of interest straddles the political boundary. So I download the Milwaukee County one. I download the Waukesha County one. I already know from just geography that they're adjacent. So I can utilize that fact and the fact that they came from the same source, meaning this, the soil survey, and I can snap them together to create one big happy vector. And then if I have to, I can extract things out from there. So you can see you have one on the left here, one on the right here, and then all of a sudden you got one big happy vector. Now let's just say, for example, my area of interest kind of goes like this, right? It's right over the border. So I could create a polygon here and in the shape of my area of interest, and then use the clip tool to chop out just everything that's underneath in this area. That way, but I had to merge them together in order to do that. Now merging combines all the features into a new feature class. That's the way I strongly suggest doing it. So you have a feature class A, a feature class B, and you're taking them and merging them together. You're not messing with the original data. You're creating a brand new data set with both of them smushed together. It's definitely the way to go for this type of exercise. So if you're trying to merge data sets together and they're typically you have to have all of your attributes identical. However, there are rare instances where that's not going to be the case. That doesn't mean you can't merge them, but what you have to do is manually tell the merge tool match up column in this one with this column in the second one. And for example, here we have the formation name. We know what that is, but in the second one, it's called unit. It's the same information, and they're just called the attribute columns are called something different. So you have to manually tell the program that, and then that way the merge can go forward. This doesn't happen very often, and it's the kind of thing where luckily with the merge tool, you're creating a new output, so you're not messing with the original. So if something gets screwed up, you just delete it and try it again. It's a bit of a trial and error thing. It takes practice because this isn't something you're going to do very often. Again, this is typically done has to be done if you have data that are from different sources. If you're using soil data, for example, like in the previous slide, they should have the same identical columns in them. So you probably don't need to do this at all. The other option, and the one I really don't recommend, is appending. So you have data set 1 here and data set 2 here. What it does is it takes data set 2 and gloms it on, attaches it, appends it to data set 1. So you're actually changing the original data, okay? And no field mapping is available whatsoever. So they better match. If they don't match, they'll get dropped. And so this is again one of those things that if you need to do it, you can. Merging is probably the better option because you're not messing with the original data. And I would strongly suggest, like the define projection tool I mentioned in the last chapter, make a copy of the original before you do an append. So generalizing data is something that is done quite often in GIS or in geography, cartography in general. It de-emphasizes certain aspects of your map, which yes, you do lose precision and accuracy. That there's no doubt about that. But sometimes you want this for a couple reasons to simplify it just visually. You don't, sometimes people get bogged down in the details, and to reduce file size sometimes or display when you're looking at large areas or small scales. So there are reasons to do this. And I nobody likes to de-emphasize data. We all want, the most accurate high resolution data we can get. But the problem with that is there's trade-offs. And if let's say I'm looking at all the United States, I don't necessarily need all of that gory detail along the East Coast of like Maine and all those places. Another common tool that's used in GIS is what's called dissolving. Many times you'll get polygons and you'll have zillions of them in hundreds of thousands of polygons in your attribute table. And what that can do is it can really bog down things, especially for displays, because it has to render all of those. Another aspect of this is if I'm converting from raster to polygon, it'll bring in every single little polygon. So what you can do is you can dissolve it. So let's say if you look at B here, you have all these little polygons. There's a ton of these little polygons, but they all have the same value. So what would be nice is to have one polygon, one big polygon with the same value as in my attribute table. So once you dissolve it, this is all the same. Even though there's different pieces, it's one row in your attribute table. So I don't know how many are in here. So let's say there's 20 rows in this attribute table. There's one here. This is a huge help. Okay. I've literally taken attribute tables from hundreds of thousands down to like 10. It's just it's a huge help for just simplifying your attribute table, because you don't need all those little polygons. The little polygons aren't telling you the story. You just, maybe you want the area of all of them. By dissolving them, you get one row that tells you the area. Boom, done. Now, one of the things that is the downsides of dissolving is you can dissolve on only one, you could dissolve on multiple attributes, but typically you're only going to do one, and then you can run some statistics as well. So you do lose some information on this, but then again, you can run the dissolve on other attributes as well and figure out other statistics. But just know that when you run this tool, you're typically going to get back one attribute at a time. And I strongly suggest only running it one at a time, because it can really confuse you otherwise. Like I've mentioned several times, metadata is data about the data. It comes with the data. It's a separate file that's in the directory structure, and it gives you all the information you need about the data. Now, I fully admit I'm not very good at updating my metadata. I admit that, because I'm more of an analyst. But somebody out there, there are people out there that are updating this stuff, and it is a huge help. It absolutely is a huge help, because you should document what you're doing to the data. And I haven't had time to, like go back and redo things, but I know going forward, I'm actually going to start doing this more, especially with my terroir stuff. So I not only does somebody else know what I did, I can remember what I did too. Because again, being an educator and trying to do research, there'll be long stretches where I don't have time to touch research, and I all of a sudden I got to go back and remember what I did. So it's always nice to have some, these are just basically notes, but they're very, very helpful notes that'll help you in the long run. So things like it'll have tags, search tags. So if you add tags, other people can search for your data if you make it publishable or shareable. Summary, just a brief description of what the data is, or a longer description, right? Really go in depth as to what's going on, how it was created, what it does or what it means, it things like that. Credits, who did it, who created it, who gets credit for it. Are there use limitations? Can anybody use this data, or is it, sensitive and it's got to be classified, right? Um, the appropriate scale range. If I'm making this data at 1 to 24,000, I'm going to put that in there. It should be used at 1 to 24,000. Again, that goes back to knowing which data to download for the scale that you're trying to work with. And finally, the bounding box. Um, this is kind of important sometimes, because when you go to certain websites and you're trying to download data, sometimes you don't know, it's not readily apparent if you download the data, is it fit within my area of interest? So sometimes you just got to look at the bounding box and go, oh, that's outside the area where I need it, or boom, I nailed it, it's right inside where I need it. So the bounding box, that's what it does. So there are different types of data used in ArcGIS, right? There's the field type, which is a description. There's shapefiles. Shapefiles are an older format. When I first started in 2003, shapefiles were the new file format, and they sit outside of a geodatabase. They're not in a geodatabase. Therefore, they don't have some of the added benefits of being in a geodatabase. Um, and then you have coverages, which are really, really old. They're not even supported anymore in ArcGIS Pro. You pretty much just got to convert them right away. There's a tool for that. Convert them to a feature class. Now, geodatabases are the way to go, period, and end of story. Even the simplest functionality of a geodatabase makes doing GIS much, much easier. Things like maintaining lengths and areas for you without having to do any math or recalculating anything. That alone makes geodatabases absolutely essential for any and all analysis. You have database connections, especially with ArcGIS Pro. You have what's called the portals, and you can connect your computer, so to speak, your into other people's shareable data and bring them into your map. You have layer files. A layer file is, I think I mentioned it earlier, that you can save all of your labeling and symbology as a layer file as long as you keep it with the original data that you made it for, and you can reuse that symbology and labeling over and over and over again. You have tables. Tables are always there, not attribute tables. A lot of times you bring in data as what's called a standalone table. It's an external table, like an Excel spreadsheet can be, turned into a table, so to speak. You have TINs, which are triangulated irregular networks used for 3D, and then CAD drawings, which we won't use at all in this course, but computer aided drafting, you can view them, but they can't be edited in ArcGIS. So the geodatabase format is by far and away what you should be using, period, end of story. It's been that way since, version 9, I think. Um, and now in ArcGIS Pro, it's pretty much mandatory. When you create a new project in ArcGIS Pro, it automatically creates a geodatabase for you. Okay, sort of a default one. You don't have to use it, but it's there. It creates all the structure stuff for you. And what geodatabases do is they allow you to put pretty much anything you want in them. So feature classes, rasters, tables, annotation, all kinds of stuff. All right. So, and then the geodatabase is stored in a folder, which should only contain the geodatabase sets created by GIS. So don't garbage up those folders. Keep things separate. Keep them organized. And this allows you to later on, if you need to, zip that folder to share it with other people. So there's three main types of geodatabases. There's sort of the old version, what are called personal geodatabases. So when they first started uh, converting over to geodatabases, this was the first one that kind of came into being. It's basically a Microsoft Access database. It's for single users, and it had a 2 GB limitation. So needless to say, we're not going to use these. And you can see right there in parentheses that it's not even recognized by Pro. They've been distancing themselves from the whole Microsoft thing for database management. Then you have what's called file geodatabases. This is what we'll be using. Um, they're stored as files in a geodatabase. They're for single users or small work groups. It's platform independent and pretty much unlimited storage. You can put pretty much anything you want in there. And then finally, you have enterprise geodatabases. This requires server space. Um, obviously, you got to pay for all this stuff. It's a commercial database management system such as Oracle or SQL Server. It's designed for multiple users and large work groups. You can do multi-user editing, versioning, things like that. That's a much higher license level, and obviously requires an admin and all this to take care of it. So we're not going to be doing that. We will exclusively be using the file geodatabases. So kind of going back in time, you still have shapefiles floating around out there, and there's quite a few of them actually, and there's nothing wrong with them per se. However, you do want to just get in the habit of right away importing them into your geodatabase. That doesn't mean, like I said, you can use them, but you want to bring them into a geodatabase. So it's basically a spaghetti format in a simple structure. They can be read by many programs. Some of the open source GIS programs like QGIS, they'll read shapefiles. Um, so you have to make sure that you kind of be careful with these because you are relegated to exactly what's in the attribute table, for example. You got to keep the name short as it says in here. But one of the things that it does not do is it does not maintain um, lengths and areas. All right, so that's there. There might be an area or a length field in the attribute table, but you don't know if it's correct because I can chop these things up in half and it doesn't recalculate anything for me, whereas a feature class sitting in a geodatabase will. So we're going to try to avoid shapefiles. In fact, you won't use these at all for your final project. If you do have to download shapefiles, you just import them in your GIS. It's not a big deal. Now, one of the things I want to show you here is a very, very important facet of GIS. And what I mean by that is never, ever, ever mess around with the data structure in Windows. Okay, so if I open a folder with a shapefile in it and look at it just in Windows without ArcMap even open, this is what you could see. So here's the parcels shapefile, and you could see there's 1, 2, 3, 4, 5, 6, 7 different files sitting on my hard drive, right? Any one of those, if any one of those is missing, you just corrupted your data. Okay, they all have to be present for this to work. Now, if you look at this in the catalog tab, this is all you're going to see is a parcels.shp file. Now, don't get confused like I did when I first started learning because no one told me. You'll see here's parcel.shp. And what I used to do, back in 2003 before I knew better, was I would grab that one and then move it and wonder why it got corrupted. Well, you have to have all of these files. You have to have every single one of these files for that one to display properly. The DBF file here, that is the attribute table. The PRJ file is the projection information. I always forget what SBN and SBX is. I honestly don't ever remember that. You have XML file, which is the metadata, and the SHX. Again, I always forget what those are, but they're all required. I think it has to do with the actual table that places it on the screen, so to speak. If you delete any one of these by accident, you just corrupted your data. So the moral of this story is never move, edit, or delete data in Windows. Okay, move things around in ArcGIS unless if you're moving entire folders, that you can get away with. But individual files, never, ever, ever, ever. Move whole folder directory structures, that's okay, just not individual files. Let ArcGIS handle that. Now, a coverage format is even older. This goes way back, and it's not even recognized by ArcGIS Pro. So I'm not going to dwell on it. I just want you to see that there is this really old file format. There's a tool in the toolbox that'll allow you to convert this straight into, I think, a shapefile. I think you can convert it to a shapefile or a geodatabase. So that's what you would do right away. Now, one of the reasons why I don't allow students to do final projects outside of the US is at least years ago, maybe not so much anymore, probably, but a lot of the data that you would find overseas in Europe and things like that, they were all coverages. They hadn't caught up yet with the newer standards, and that became a real pain. So that's why I just don't allow it. Um, and plus, it's just easier because unless if you speak the language, a lot of those websites are in foreign languages and everything else. So if you ever had to come across something like this, your first instinct would be just convert it right away. Don't even bother. It's not worth it. It's a super old format that nobody uses anymore. So you can connect ArcGIS Pro to what are called relational database management systems that contain non-spatial data. That's pretty cool. That's a new feature kind of thing. Stuff like if you just have a database management system sitting out there for a business, even though there's no geographic component to it, you can still connect to it with all the proper credentials and everything with ArcGIS Pro. So that's pretty cool. You can connect to public databases or those requiring a login, like I just mentioned. So, and I briefly said before, you can read and display CAD files, but you can't edit them. So that's, but again, we're not going to do any CAD stuff. That's more for the urban planning people. You can often, nowadays, the whole attitude with GIS is sharing, getting it out online, publishing it, letting other people see it, letting them use it if it's applicable. But you want, the whole online presence, the cloud structure, and everything else is a lot different than just 5, 6, 7 years ago. So this is one of those things that I'm hoping to incorporate in this class if I have time to do it. But going forward, we're going to try to utilize ArcGIS Online a little bit, if nothing else, just to show you what's out there. Because we're within the UWM confines, you automatically get a login to ArcGIS Online, which would allow you to upload, let's say, a final project to it and share it with others if you wanted to. I believe chapter 12 deals with that a little bit. Now, if you're not used to doing any type of computer work, if the extent of your computer work is Facebook or social media, you could get really confused sometimes with when I start talking about things like directory structures and path names. Um, Me coming from the Unix Linux world, it's just second nature for me now. But I understand not everybody understands that. So the idea is you have to know where your data is sitting. And not only do you have to know where it's sitting, you want to place it in a place put it in a place that you can easily get to without, any type of permission restrictions, and to keep path names short and no spaces. Remember, I already mentioned that. You don't want spaces in your path name. So one of the things that you do is put it right on the C drive. So here's a path, right? Think of it kind of like a URL. You could think of it that way too. So I'm on the C drive. I'm in the GIS class folder, the MGIS data folder, the Oregon folder, the Oregon data folder, and then the counties. So you have to understand this directory structure. And if you don't, it's not hard to figure out. You can do this by opening up a folder in Windows or on a Mac and just kind of going up and down, so to speak. So click on a folder within a folder within a folder within a folder, and then back out of that, you start to see the pattern of, oh, this is where I am. And it shows you up on top as well. Okay, so if it starts with a drive letter like this is what's called an absolute path. It's exactly where it says it is on that particular hard drive. Now I have multiple hard drives, so sometimes I use these in order to remember where all my data is sitting. But in general, what you'd like to do is use what are called relative paths, okay? And what that is if I add data to my map, let's say here, the county's data, and I have another folder one level up that's called roads, I can add that, and the program knows that I just got to go up one level to the roads and get the data there. So by default, they are assigned automatically in ArcGIS Pro. So it knows if you're connecting to some hard drive level or it's a relative path compared to the other data on your map. I know this can be a bit confusing at first, but pay attention to where you are in the directory structure, and over time this just becomes second nature. It's probably something you might already know and you just never realized what it was. Um, but if you have your computer at home, you probably somewhere on your computer have one full of pictures, and maybe within that folder you have a picture or folders of various events, let's say a wedding or an anniversary or a birthday. So you're subdividing your folders, and so you're drilling down into those folders. So we start at the C level, you go into GIS, the GIS folder, and then the MGIS folder, the Oregon folder, and then there's a geodatabase in there. And you can double click on the geodatabase because a geodatabase is what I consider just a big fancy folder for the most part for what we're doing. We're not utilizing all the topological things that you can do in there and all of the bells and whistles that a geodatabase is capable of. For us, it's a fancy folder to put our data in that maintains things like lengths and areas. So, excuse me, ArcGIS Pro assigns the path name automatically. Usually it's for relative paths for a local hard drive, which makes sense because then that way it's easier to go up and down in levels. Or absolute paths for a network file server. So if you're bringing in data from, let's say, a portal somewhere out on the web or in the cloud, then yeah, it's going to assign a hard drive, or excuse me, an absolute path for that. Um, or a UNC path for internet data services. That would be something outside, like I mentioned, the portal that you have nothing to do with. Let's say you connect to the NOAA website for precipitation data. So it understands that to this assign a UNC path, which is a unified network. I forgot what that stands for, but um, so you just got to be careful. And if you're going to copy projects, okay, now remember ArcGIS Pro uses project folders now. You copy the entire folder, not just the .aprx file. Now the .aprx file is the equivalent of the old .mxd file in old ArcMap. In ArcGIS Pro, it's sort of your map file. Okay, it's the ArcGIS project file. So it sort of encompasses everything. It sort of takes over for the .mxd file. So rather than just taking that file and copying it, you want to take the whole file the whole file structure instead. And there's a reason for this, which I'll get to in the next slide. So if you take the map file, the .aprx file, and move it without moving the data with it, you'll get what I call the dreaded red exclamation points. So what that means is if you see this in your table of contents area here, if you see these red exclamation points, okay, what that's saying is the link between the map and the data has been broken. Okay, the map can't find where the data is now. It thinks it knows where it is, but you either deleted it or you moved it. And if you moved it, then you have to retell the map where it is sitting now. Okay? And you can it's not a big deal to fix this, but you have to know that you're going to have to fix it if you move one, either if you move the map or if you move the data, this is going to occur. So in what you want to do is if you're going to move things, you want to move them en masse. You let's say zip up the whole folder structure and zip the whole thing up rather than just the one file. All right. So and the other part of that is you don't want to rename projects, okay? Because that way you don't you can lose track of internal components. ArcGIS Pro has a much more complicated structure than the old ArcMap does. So when you create a blank project, it's actually creating numerous things. It's creating a geodatabase, a ArcPy table, toolbox. It's creating an index thing so it can quickly get to in and around your folder files. So it's doing a lot of things in the background. So you don't want to A, use spaces, and B, rename things without if you can help it. So that's why you want to keep a naming pattern, keep a name structure, and stick with it till the very end, so to speak. Now, we're going to talk about this briefly, but we're going to get more into this later in the semester. One of the absolute best things you can do when you're especially working on your final project is set up what's called environment variables. You have all done this at some point in time, but in other programs, it's called settings, right? It's called preferences, depending on what you're using. In ArcGIS and ArcGIS Pro, they're called environment settings. What this does is it allows you to set up the features so you know exactly what's going to happen every time you either run a tool or save a map or these kinds of things. So, for example, when I run a tool, I can specify exactly where the output's going to go. That's huge. That way I don't always have to fill out the dialog box every time I run a tool. What the output coordinate system is going to be. This should be just hopefully obvious by now. If you're doing a final project, you want all of your data in the final the same projection, right? It's a requirement for my project. You would set this up so every time you run a tool, you don't have to run the project tool. It's automatically being saved as the output into the coordinate system of your that you desire. And that is huge, 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 huge when you're doing analysis. So it takes all the guesswork out of having to worry about which projection you're using because you set that up ahead of time. You tell it every time I run a tool, this is the output coordinate system. This is where I'm going to save it. Now, there are two levels of environment settings. You have the tool level, okay? So when I run a tool, it'll run those specific criteria that I set it to. I don't, I strongly recommend not doing this, okay? If you're running a project, if you're doing a project, you know already what your coordinate system is going to be. You know where you're going to save your data. You probably have everything set up and nice and neat and tidy, I hope. So you know where things are going to be. What you would do is you would run it at the application level. That was a horrible line, sorry. At the application level. So what that means is it's going to run everything that you run the same exact way. It'll always be put where you want it to be output to go. It'll always be in the coordinate system. When we get to rasters, you can specify the cell size, which is huge, because that should match your digital elevation model, your DEM. All right. So you already can set these ahead of time. So no matter what tool you use, what tool you run, you already know these things are going to occur. Because the last thing you want to do is run a whole bunch of tools, get a bunch of output, and then have to run the project tool on all of them. That would suck. You wouldn't want to do that. This is a huge, huge time saver. So just remember when we get down to geoprocessing, we'll talk about this more, but this is basically setting the preferences for your program to save time. You would do this for every map. So and it saves for every map, so to speak. So the environment settings I set for this project work for this project. If I start a new project, I can set those again and they will be set for that project. They don't overlap. So one of the first things you should absolutely do, and I've mentioned this already, is when you're doing your project, you have to come up with a coordinate system that you're going to work with. And you stick with that one coordinate system. And then you have to also figure out which datum you're going to use. Am I going to use NAD83, NAD27, NAD83 HARN, WGS84? Once you have that, you can set those environment variables fairly quickly to ensure that every single time you generate output from whatever tool you're using will automatically be in the coordinate system you want. Remember, for your final projects, I grade all of that. I look at every single one of your uh, feature classes that are on your map, and I make sure that they're all in the same coordinate system. Now in ArcGIS Pro, they've added this new thing where you can actually view all of your data based upon its coordinate system, and this is really cool. And this will be a good way for you to understand, hey, did I miss something? So you'll notice here's NAD83 State Plane, New Jersey. All of these are in the same coordinate system, right? Then you have this one down here. This is a base map. So by default, the base maps use that WGS84 Mercator auxiliary. I do not want base maps for your final projects, okay? So everything should be in the same coordinate system. If you have anything else in this layer, then you know you missed something. You need to either reproject it or project it the first time, so you don't get points taken off for that. This is a great addition to ArcGIS Pro. It's a quick visualization to understand, hey, is all my data in the same exact coordinate system? All right, so that brings us to the end of chapter 5. So this is a new chapter for the book. She kind of separated some things out. It's nothing that I haven't discussed in previous versions of the book, but she kind of took this out for vectors. So chapter 6, looking ahead, is going to be the same sort of thing, sort of the do's and don'ts with raster data. So chapter 6 is managing raster data. I love rasters. It's my bread and butter. It's what I do. It's what I love. It's what makes GIS fun. For me personally, there's a lot of things that make GIS fun, but I love raster work, LiDAR and elevations and precipitations and kriging and overlay and all this fun stuff, which we'll get to later on in the semester. So chapter 6 is similar to chapter 5 in the sense that it'll be the do's and don'ts for raster work. And stay tuned. We'll see you soon.